So now let's come back to this idea of examining our one-sided limit. And we use this notation right here, c from the left, c from the right. And we're looking at this idea that says that if we have a two-sided limit, one of the things that we stated was that uh, the limit as x approaches c of some function f of x exists if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. In other words, these two limits have to meet and they have to agree. So in this particular example, the two-sided limit fails to exist even if the limit from the left and the limit from the right exist by themselves. So let's look at an example right here where we're going to be talking about these things. And I have two different examples. Let's just deal with one at a time. The first example I want to look at is this one. Let's just talk about a one-sided limit. We might be asked to say, evaluate the limit as x approaches 5 from the right. And we've got an expression like this one. The limit as x approaches 5 of the absolute value of x minus 5 over x minus 5. Now, in this case, this is where you have to remember a little bit of a definition about your absolute value. So let's go back. Remember, we said the absolute value of any quantity is either equal to itself if that quantity is greater than or equal to 0, or the opposite of that quantity if that quantity is less than 0. So if we're saying we're taking the limit as x approaches 5, this means, it implies that the values of x that we're going to be using right here are values of x that are greater than 5. Even if we say very, very close to 5, like 5.01 or 5.001, x is going to approach 5 from the right. So we can rewrite our limit and say, well, this is really the same thing as the limit as x approaches 5 from the right of x minus 5, the positive of x minus 5 over x minus 5. Well, as long as x does not equal 5, right? As long as x does not equal to 5, this is really the same thing as the limit as x approaches 5 from the right of positive 1. And we know that the limit of a constant is simply equal to the constant. And remember, it doesn't really matter that at x equals 5, this expression is indeterminate, because the limit does not, the value of the limit does not depend on the value of the function at that point. So we can say that this is our limit from the right. That's it. Now, as an exercise, evaluate this limit as x approaches 5 from the left and see what happens. How's our second example? We've got a second example. This time we've got another piecewise function where we would want to examine what is the limit as x approaches 2. And we have this principle, again, that says the limit as x approaches c of f of x exists if the limit from the left is equal to the limit from the right. So that means what we're going to have to do is we're going to have to evaluate two different limits. We're going to have to evaluate our limit as x approaches 2 from the right of f of x, of course. That is the point right over here where x is greater than 2. And then, of course, we want to evaluate our limit as x approaches 2, this time from the left of f of x. So we're going to have to compare these two, and that's this portion right up here, right? Because we're talking about the behavior when x is to the less than 2. All right, so let's look at the first one up here. The limit as x approaches 2 from the left. Well, in this case, evaluating this limit, we let x approach 2 from the left of the expression x squared minus 4x plus 6. Now, the nice thing about this is that we are back in polynomial territory. We're only evaluating it from the left-hand side, but that's okay, because by substitution we would find that this is defined 2 squared minus 4 times 2 plus 6, and working that out, that's 4 minus 8 plus 6. 4 minus 8 is negative 4 plus 6. That gives us positive 2. Now let's look at what happens as we come in from the right. This time we're going to be taking the limit as x approaches 2 from values that are slightly greater than 2 of the expression negative x squared plus 4x minus 2. And let's see what happens. Again, because this is a polynomial style of function, we can evaluate this by substitution. So that's going to be the negative of 2 squared plus 4 times 2. I'm writing that kind of funny here. Minus 2. Working this out, this is the negative of 4 plus 8 minus 2. If we go negative 4 plus 8, we get 4 minus 2. We get 2. So, lo and behold, if we're asked to evaluate the limit as x approaches 2 of f of x, we can say that since these two things match, the limit as x approaches 2 of f of x itself is equal to 2. And the limit exists. Right? So if you have that kind of function, we can also talk about the continuity there. Right? What would happen? Well, f of 2 itself, evaluating our function right here, we know by substitution that's negative of 2 squared plus 4 times 2. There you go, writing it really funny again. 4 times 2 minus 2. Pardon me, let's make that look right. That's minus 4 plus 8. Wow. Boy, this got a leaky pen today here. Let me try it again. Negative 4 plus 8 minus 2, and sure enough, that's equal to 2. And so since f of 2 is equal to 2, and the limit as x approaches 2 of f of x is equal to 2, we know that the limit as x approaches 2 of f of x is equal to f of 2, and therefore we could also add one other item here, even though we weren't asked it, that f of x is continuous. At x equals 2. Very interesting.